Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics in the chapters of energy and linear momentum. This exercise was a previous one in the Terminal LS exams 2016 second session, second exercise. The title of this exercise is Nature of a Collision. The aim of this exercise is to determine the nature of a collision between two objects. For this aim, an object A, considered as a particle of mass m, ma is equal to 2 kilograms. Then let me write here that the mass of the object A is given by 2 kilograms. Can slide without friction on a path situated in a vertical plane and formed of two parts, a circular part dn and a horizontal rectilinear part nm. So they are talking about figure 1, and at the moment they mentioned without friction, so from d to n and n to m we don't have friction, then the mechanical energy in this case is conserved. Now they are telling us that A is released without initial velocity. Then we know that initially so we have that VA 0 is equal to 0, and this is because it's released without initial velocity. Now from the point T situated at a height ht is equal to 0.45 meters, then let me write here that the height at the point D is equal to 0.45 meters. Above the horizontal part nm, figure 1. Now the horizontal plane passing through Mn is taken as the reference level of a gravitational potential energy. So this is the PE level, which is the horizontal plane passing through Mn, which is the x-axis, and we have that g is equal to 10 meter per second square. So this is the gravitational acceleration. Now in number 1 they are telling us to calculate the mechanical energy of the system A Earth at the point D. And we know that the mechanical energy is the sum of kinetic and potential. So here we are calculating the mechanical energy of the system A Earth. So this is for the object A at the point D. So let me say that this is 80. And at the point D, we know that A initially has no velocity. So in this case, we know that the kinetic energy of A at the point D is equal to 0. And this is because no initial speed. So in this case, this is equal to 0. And the energy is purely potential, which is equal to mgh, and here we are talking about the gravitational potential energy. So the mass of the object A, which is given by ma, and the height at the point D, which is given by hd. Now this is equal to 2 multiplied by 10. And notice that in this case, because we are measuring the height above the P level, so the height is positive, multiplied by 0.45, plugging this on the calculator, then the mechanical energy of the system A Earth is given by 9, since everything is expressed in the SI. So the value of the mechanical energy will be in the SI, which is joules. So here we can safely write that the mechanical energy of A at the point D is equal to 9 joules. Now in number 2 they are telling us deduce the speed v1a of A when it reaches the point n, and by deduce it means that we need to use the previous part. In the previous part we have determined the mechanical energy of the system or of A at the point D, and we are asked to deduce its speed at the point n, and this is done by the conservation of energy, because from D to n there is no friction, and as A moves from D to n there is a conversion from potential to kinetic. So let me say, since there is no friction, then the mechanical energy of the system and this system we are talking about the system which is given by A Earth. So here it's important that we mention the system we are working with is conserved. So the mechanical energy of A at the point D is equal to the mechanical energy of A at the point N. So let me say that the mechanical energy of A at the point N is equal to the mechanical energy, which is equal to the mechanical energy of A at the point D, but eventually we have calculated this and it's given by 9, so here let me write 9. Now recall that you are interested in determining the value of the speed, which is encoded here at the level of the kinetic energy. So the mechanic is always purely kinetic and potential. This is equal to 9, and we are interested in determining this value. And here, luckily, this is equal to 0. And the reason is that at the point N, A will pass through the PE level, so passing through the PE level. So this is 0. Now the kinetic energy of A at the point M is given by quadratic in speed, which is given by half ma, and the speed is denoted by v1a, so this is v1a square, which is equal to 9, and we are interested in determining this. So v square 1a is equal to 9 multiplied by 2 divided by the mass of A, which is equal to 9 multiplied by 2 divided by 2, which is equal to 9. So here, this is the value of v square. Now we are interested in determining v1a. So in this case, v1a is given by the square root of 9, which is equal to 3. Now everything is expressed in the SI, so the unit of v1a will be meters per second, which is the SI. So we know that the speed of A at the point N is given by 3 meters per second. And here let me say the following remark. Notice that here I didn't place any unit, because this is not given by meters per second, but however, because this is the power 2, then it will be by meter square and second square. So if we need to place the unit, we must place it correctly. So I highly recommend that always we place the unit for the final answer. Now regarding part 3, they are telling us that A reaches N and moves along an M with a speed with the same velocity v1a. So as A reaches the point N, it continues its path with the same speed that we have determined. Now another object B, which is situated between N and M, so consider as a particle of mass M is equal to 4 kilograms. Moves along the horizontal path from M towards N, so B is moving like this, with a velocity v1b is equal to minus 1i, so it is expressed in meters per second, and the minus sign to indicate that it's moving from M to N. So let me say that here v1b is equal to 1 meters per second. Let me make some space. Now we are in 3 part A. They're asking us to determine the linear momentum PS of the system AB before collision. So as A is moving from N to M and B is moving from M to N, yet they didn't collide, so we can determine the linear momentum of the system. And the linear momentum of the system is simply the linear momentum of the first object and the linear momentum of the second object. Now here, this is the linear momentum for A, and this is the linear momentum of B. And usually linear momentums carry the same indices of the speeds. So since this is 1A, then this will be 1A, or the same labels. And this is 1B, this will be 1. And notice that here in the question they are telling us to calculate P as vector. So we need to calculate it in the vector notation, no need to project. Now P1A is the linear momentum of A, which is given by the mass multiplied by the velocity, then it's given by ma multiplied by v1a, and here the vector quantity, which is the velocity, so the vector must be above the velocity. And regarding P1b, it is the linear momentum of V, so it's the mass of B multiplied by V1B. Now this is equal to, now the mass of the object A is given by 2, and the velocity is given by 3, so this is the magnitude, but notice that it's moving along the x-axis from n to m in the positive direction, so it's simply plus 3I. Now regarding the linear momentum of B, its mass is given by 4, and as for, so let me write brackets, and as for its velocity, its magnitude is given by 1, but it's moving in the negative direction from m to n, so it will gain a minus sign, so this is minus 1I, so this is equal to 6I minus 4I, so which is equal to 2I. And because all quantities in physics must have unit, so the unit of the linear momentum, we know that it's given by kilogram meters per second, so this is the final answer. So although A is moving toward the right, B is moving toward the left, taking into consideration the mass and the speed, so this system can be replaced by a point mass, which is the center of gravity, moving from left to right with the following linear momentum. Now in part B, they are telling us to deduce the velocity Vg of the center of inertia G of the system AB, and by deduce it means that we notice the previous part. In the previous part we have determined the linear momentum on the system. We know that the linear momentum of the system can be calculated using this way, which is the sum of the first of the two, or it can be determined by via the velocity of the center of inertia G, because we know that another formula for the linear momentum of the system is given by PS, which is equal to the mass of each object, MA plus MB, and multiplied by Vg, which is the velocity of the center of mass or the center of inertia, and in this case we are interested in determining Vg. So whenever we are dealing with vector equations, we need to be very careful. Recall that we cannot multiply or divide by vectors. However, this is a scalar, which means it is a number, so we can divide both sides by this quantity. So in this case, Vg is equal to 1 divided by MA, or let me say this is PS, divided by the mass of both objects combined. Now PS is given by 2 multiplied by the unit vector I, and the mass of the first object is given by 2 and the second is given by 4. So here we have the 2 plus 4, which is equal to 2 divided by 6 multiplied by the unit vector I, which is equal to 1 over 3 multiplied by the unit vector I, and because everything is expressed in the SI, so this will be in meters per second. So the velocity of the center of inertia of G of the system is given by, so this is almost equal to 0.33 meters per second. So here, because they asked to calculate it in the vector quantity, for this reason we didn't project any of the values. Now in number 4, they are telling us that after collision, A rebounds and attains a maximum height. HC is given by 0.27 meters. So here what will happen is the following. Now yet A and B didn't collide. After they collide, so we expect that B, so okay, so what will happen that A, they are telling us that after collision A rebounds. So A rebounds means that A previously was moving from N to M. After it collides with B, now it will move from M to N and rebounds back, so it moves back. And after it moves back and reaches the point N again, it will go up along this plane and D, and it will reaches the point C, and the height of C is given by HC, which is equal to 0.27 meters. Now in part A, they are telling us to determine the mechanical energy of the system A Earth at the point C. So the mechanical energy of A, but now at the point C, is equal to the kinetic energy of A at the point C plus the potential energy of A at the point C. And here, notice that they are telling us that it attains a maximum height, and we know that whenever the position is maximum or the height is maximum, then the speed is 0. So let me say that between brackets that the kinetic energy of A at the point C is equal to 0. So whenever we talk about the kinetic energy, it means a speed, and in this case the reason is given by maximum height. So this is 0, and now this is equal to the mass of A multiplied by G multiplied by the height at the point C, and now this is equal to, so the value of MA is given by 2, the value of G is given by 10, and the height at the point C is given by 0.27. Now plugging this on the calculator, then the value of the mechanical energy of A at the point C is given by 5.4 joules. And here let me make some space, we are done with this. And now we are in part B. They are telling us deduce the speed v2a of A just after the collision, and by deduce it means that we notice the previous part. In the previous part you have determined the mechanical energy of the system A Earth at the point C, and eventually we can deduce the speed of A just after the collision. Because why? Here remember that we don't have friction, since now we know the mechanical energy of A at the point C, so we can deduce the speed of the point A just after leaving the point N, which is after the collision. Okay, so remember that after they collide with each other, so A will go back and move from N to C, so we know the mechanical energy at the point C. Now we can deduce again the mechanical energy at the point N. So here let me say that since there is no friction, then the mechanical energy of the system, and we need to specify the system that we are working with, and this system is given by, so let me make some space. A Earth is conserved. So here we are talking, okay, so we are talking about the mechanical energy of A Earth. Then the mechanical energy of A at the point C is equal to a constant, the mechanical energy of A at the point N is equal to the mechanical energy of A at the point C that we have predetermined, and it's given by 5.4 joules. And we are interested in determining the speed at the point N, which is encoded in the kinetic energy. So the kinetic energy of A at the point N plus the potential energy of A at the point N is equal to 5.4, and here between the brackets we can say that the potential energy of A at the point N is equal to 0, and the reason is given by passing through the P level. And the kinetic energy of A at the point N is given by half ma. Now we need to use the same notation. The speed is given by v2a, which is equal to 5.4, and we are interested in determining this value. So if we rearrange for v2a squared, then v2a squared is equal to 2 multiplied by 5.4 divided by ma, which is equal to 2 multiplied by 5.4 divided by the mass of A, which is given by 2, which is equal to 5.4, and this is the value of v2a squared. So in this case v2a would be given by the square root of 5.4. Now I'm plugging this on the calculator, then the speed of A at the point v2a, which is the speed of A at the point N after the rebound, after the collision, is given by 2.323, since everything is expressed in the SI, then this will be expressed in the SI, which is given by meters per second. And notice that here I didn't place any unit because this is v squared. So here if we would like to place a unit or to write a unit, then this is given by meter square per second square. So let me write that v2a is given by 2.323 meters per second. Now in number 5 they are telling us determine by applying the principle of the conservation of linear momentum of the system. Then let me write as a title that during collision the linear momentum of the system. So always we need to specify the system that we are working with, and here the system consists of the two objects A and B. Is conserved, and by applying this principle we need to determine V2B. So let's do a recap about what's happening during collision. So previously A reaches the point N from D and it collides with B. So this is A. So previously A was moving with speed with the velocity v1A, and B was moving from M to N with the speed given by v1B. So in this case, so let me say that the initial linear momentum of the system is equal to the final linear momentum of the system. So initially Pi is given by, so P1A plus P1B. So why? Because this is V1A of the object A, and this is V1B, and recall that always linear momentum carry the same indices of the speeds or the velocities. Now P final would be given by, so now A rebounds back with V2A, so here we have P2A, and B, so they are telling us the velocity V2B of B just after the collision. So we suppose that B moves toward the right with the velocity of V2B. So in this case we have P2B. Now if we don't know if B, okay, for sure B in this case will move toward the right, and in this case we are interested in determining V2B, which is encoded here. So let me replace the formula of the linear momentum. So here we have MA V1A plus MB V1B, which is equal to MA V2A plus MB V2B, and we are interested in determining this one. So here notice that we are interested in determining V2B in the vector notation. So I will solve this equation using the projection method, but there is another way in which one can solve this equation. So let me start by the usual way, which is the projection. Then we are interested in determining this one. Then what's the type of this equation? This is a vector equation. How do you solve it? Using projection. So projection along the x-axis. So in this case we drop down all the vector quantities, and each vector quantity will carry the label x. So here we have that MA V1AX plus MB V1BX, which is equal to MA V2AX plus MB V2BX. Now x, so all of them lies along the x-axis, so no need for the cosine. So each one will carry either a plus or minus sign depending whether it's moving in the positive direction or in the negative direction. Remember that A was moving in the positive direction, so this is plus, then MA V1A. Now what about B? B previously was moving toward the left, so it will gain a minus sign, then it's given by minus MB V1B, which is equal to, now after the collision A rebounds back, so it will move in the negative direction. So here we have minus MA V2A. What about V2BX? So because we want to calculate this one, So we will not project it, we will keep it as it is. So always the one that we are determining, it will not be projected. If it's positive, then it will move in the positive direction. If it's negative, then it will move in the negative direction. And we are interested in determining this value. So let me rearrange. Here we have that MB V2Bx is equal to MA V1A minus MB V1B. Now moving this to the left hand side, it will gain another minus sign and it becomes M plus MA V2A. Now dividing both sides by MB, then V2Bx is equal to MA V1A minus MB V1B plus MA V2A divided by MB. Now let's replace the values. So the mass A is given by 2 and the speed V1A is given by 3. Now MB is given by 4 and the speed V1B is given by 1, plus the mass MA is given by 2 and the speed V2A, which we have predetermined, is given by 2.323, divided by the mass of the object B, which is given by 4. Now plugging this on the calculator, we can find that it's positive first of all, and its value is given by 1.662 meters per second, which means that B indeed will move from N to M with this value. Now recall that we need it in the vector notation, so we can say that in this case V2B in the vector notation is equal to 1.662 with the unit vector I, because here we have a vector, then here there is a vector, and the unit is given by meters per second. Now in number 6, they are telling us to specify the nature of the collision, and we know that collisions are classified as either elastic or inelastic, and this depends on the value of the kinetic energy of the system, initially and final. If it's conserved, then the type of collision is elastic, and here we expect that the collision is elastic. So let's determine the kinetic energy initial of the system. Because both A and B are in motion, then we have the kinetic energy of A, and this is given by 1A because they carry the same label of the speed, and this is given by kinetic energy of 1B, which is given by half MA V1A square plus half MB V1B square. Now let's replace the values. Here we have half 2 multiplied by 3 square, which is the mass of MA and the speed of A at the point N, plus half the mass of B, which is given by 4, and the speed, which because B was moving from M to N with the speed of 1 to the power 2. Now plugging this on the calculator, then its value is given by 11. Since everything is expressed in the SI, we know that the unit of energy is joules. Now regarding the final kinetic energy after the collision, we have kinetic energy, so it carries the same label of the speeds, which is given by 2A, and the kinetic energy of B, which is given by kinetic energy 2B. Now let's replace the formulas. We know that the kinetic energy is quadratic in speed, so MA V2A to the power 2 plus MB V2B to the power 2, which is equal to half. Now the masses are the same, but there is a rearrangement of the speed in such a way that this is 2.323, and this is given by 1.662. As you can notice that during the collision there is a redistribution of speeds, and whether plugging this on the calculator, this would give us 11 joules, and whether the collision is elastic or no, so this is almost given by 11 joules. Whether the collision is elastic or no, this depends on the value of the kinetic energy of the system. So in this case, we know that initially the kinetic energy is given by 11 joules, and finally the kinetic energy is given by 11 joules, and in this case we can say that kinetic energy initial is equal to kinetic energy final by comparison. So let me say the following reason: since kinetic energy initially is equal to kinetic energy final, then the type of collision is elastic. So that's it for me in this video, guys. See you soon in a new one.